So far in our unit on graph theory, we've been concerned with paths, how to connect different vertices, or in some cases, how to travel different edges in a specific order. Today, with lesson 15.4, we're going to kind of shift our focus. So we're not concerned so much with paths anymore, but we are focused on that idea of connectedness. How can I get from one vertex to another, but not necessarily in a specific order. So today we're going to talk about something called trees. A tree is a specific type of graph, a connected graph that has no simple circuits. That means it is not possible to start at one vertex, travel throughout your entire graph, and then end at the same vertex. We do not want that in a tree. A tree has a few important properties. The first relates to that no simple circuits idea. We have something called the unique path property. That means that there is exactly one way to get from one vertex to another vertex for any pair of vertices in my graph. So to get from here to here, I have to go this way. I don't have another option. Because I have this unique path property, there are no circuits anywhere in my graph. Even in a small portion of my graph, I have no circuits. That means that if I were to remove any of those edges in the graph, my graph would be disconnected. So my graph would be disconnected if I removed any edge. That means that every edge in a tree is a bridge. Remember, a bridge is an edge that connects two pieces. Without that bridge, our graph would be disconnected. So if I remove any edge in my graph, it's disconnected. That means every edge is a bridge. Our graph will also have a set number of edges based on its number of vertices. So if I have n vertices, let's say n is 8, I would have n minus 1 edges. So 7 edges. That's true for every tree. Now here comes some of the sort of unusual vocabulary for this lesson. So a tree is a graph that has these characteristics, fits these properties. If my graph is larger than just a single tree, and the graph itself isn't a tree, but all the little pieces of it are, my graph is essentially a collection of trees, then we call that graph a forest. So if your graph is not a tree, but it's made up of trees, it's called a forest. So collection of trees is a forest. And then here's the other weird vocab term for this section. A vertex in our graph that has a degree of 1 is called a leaf. Something out at the very edge of our tree is a leaf. So the first thing we're going to take a look at is, are these graphs trees or not? Okay, so if it's a tree, we'll identify it and circle the leaves. If it's not a tree, we'll just say not a tree. So I'm going to rely on this unique path property and n minus 1 edges idea from earlier. So if I take a look at this graph right here, if I want to get from this vertex to this vertex, I could go this way, 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 I could go this way. I've got a lot of different ways to get from one vertex to another. That means that it does not have a unique path to get from one vertex to another. And if I look, I've got 1, 2, 3, 4, 5 vertices, and 1, 2, 3, 4, 5, 6, 7, 8 edges. This is not a tree. For my second graph, let's take a look at that vertice-edge relationship here. Connected graph, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9 vertices, and 1, 2, 3, 4, 5, 6, 7, 8 edges. That fits this relationship up here. And if I want to get from one vertex to any other vertex, either I'm getting to the center one, so it's just travel that edge, or I have to travel an edge and then the edge to whatever vertex I want to get to. So this is, or this graph does have, I should say, the unique path property. This is a tree. And then we're going to circle our leaves here Remember, the leaves are the vertices that have degree of 1. Remember, degree refers to how many edges use that vertex as an endpoint. So that would be all these guys out here would have degree of 1 because they just have a single edge. So these would be all our leaves. All our vertices have degree 1. For part C, this graph is not connected, so it can't be a tree because it's not connected. But if I look at its individual parts, this portion and this portion, these are trees. This has 1, 2, 3, 4 vertices and 1, 2, 3 edges. This other part here has 1, 2, 3, 4 vertices and 1, 2, 3 edges. So this graph as a whole is not a tree, but since it's made up of trees, we could call it a forest. And then our leaves, again, would be those vertices of degree 1. So this guy here, right there, and right there. So tree, a forest, not a tree or a forest. So we take a look at trees because a lot of times what we're looking for with trees is how to figure out a way to connect different key features without necessarily having to create a path out of a larger graph. So we're going to focus on something called a spanning tree. A spanning tree is a tree within a larger graph that meets every vertex of the graph. It does not have to be a path. Okay, that's important. It does not have to be a path. So I'm just looking at how can I connect all the vertices here. And again, without any circuits or loops. I don't want to be able to go in a circle. So if I take a look at this first graph I have here, this is not a tree, right? I've got lots of circuits, lots of loops here. I just want to be able to connect all the vertices in such a way that I don't have any circuits. So you could find a spanning tree that is a path, and that's fine, but it doesn't have to be. So for example, I could have a spanning tree that looks like this. I've connected all those vertices. I have a way to get from one vertex to any other vertex in the graph. That's a spanning tree. Notice that I've included every vertex, but I've left out some edges. That's typical for a spanning tree. Same idea for B. I want to find a spanning tree. So I could travel around the outside, making sure I stop before I get back to that starting vertex. I could travel sort of that star pattern, again, making sure I stop before I return to that starting vertex. Or I could create a spanning tree that essentially branches out from one point. That would also be a spanning tree for this graph. Okay. So remember, a spanning tree does not have to be a path. It's okay if it is. So if this is your spanning tree, that's fine. Just make sure you don't go back to the start. You could have some other crazy nonsense in here too, as long as, again, you don't have a loop. You don't repeat a vertex. Every graph, every connected graph, I should say, has at least one spanning tree. And again, that spanning tree does not need to be a path. Every connected graph has at least one spanning tree.